My goal with this video today is to try to approach then this paper and see if the actual thing that I was doing the other day with Xanadu is anyhow close to Grover actually. See if that will, if the paper will allow me to figure this out. Though that's something that I don't know. So just remember this is the stuff that I was doing, um, where I was basically doing a preparation. Then these three gates are sort of the oracle. Then this is the mixer. Then again oracle or cost function and a mixer. But it seemed like one was good enough, right? But at the end of the day, that's also what one iteration was kind of good enough. But like I don't know, Grover's algorithm also when you use a small amount of qubits, you just need one iteration and it's kind of done. Um, but I wonder whether this is sort of equivalent here. Let's see. Um, so what have we got in here? So we've got a. This is how many pages? This is like 4 pages with references included, so it's also really compact. Um, okay, let's quickly. So a fast quantum search algorithm for continuous variables is presented. The result is a continuous variable analog of Grover's algorithm. Um, a continuous variable analog of the Hadamard, the Fourier transform operation, is used in conjunction with inversion about the average of quantum states to allow the approximate identification of an unknown quantum state in a way that gives a square root speedup over such algorithms using classical continuous variables. Also, we know that this quantum search algorithm is robust for a generalized Fourier transform on continuous variables. So the one difference that I note here is that we're talking about approximating a quantum state. So we're not talking, this is maybe a bit more generic, approximate identification of an unknown quantum state. Um, Quantum systems can register and process information in ways that classical systems cannot. As a result, it is possible for quantum computers to perform certain computational tasks faster than classical computers. So it's a bit of an introduction here again. These algorithms are usually implemented in quantum systems whose observables have discrete spectra, such as a collection of two-level atoms. However, the classical. Okay, so I think I was reading this. With recent years and manipulate continuous information with the recent advances in our ability to manipulate continuous quantum information interpretation, error correcting codes, and its feasibility of implementation using linear devices. Okay, so this is just okay. Can we do the same? Right, that's the question. Um, this slide will propose a fast quantum search algorithm with continuous variables. Here, continuous variable can be anything: position, momentum, energy. I feel like I went through this. I think actually, yeah, when I did the quick, when I did it, or not. I don't know. It feels like I went through this. So let me get some brightness in my screen here. Yeah, I feel like I've read through that introduction quickly. Here we discuss how to perform a quantum search algorithm with continuous variables. First, we need to map a conventional discrete search problem into a continuous variable context. Suppose we have a function. Yeah, I was reading through that. I thought I was what? Okay, let me check. Our task is to discover the value kf. Okay, to inputs and given no further information on the function fk. In order to implement this in a quantum computer with continuous variables, we require a collection of n qnats. Yeah, I was reading that, but is it then that I just stopped somewhere? So this is basically if one exploits the power of quantum superposition and entanglement, however fewer function calls are required, our approach is discussed below. collection of n continuous variables whose Hilbert space is spanned by a basis states satisfying the orthogonality condition. For example, one can consider a compact region of the state space divided into n equals volumes, each with measure. Collection of n variables whose Hilbert space is spanned by a basis of states. Blah. So, which means, okay. In the context of this continuous variable embedding, executing the function f corresponds to adjoining an extra state to the system. Clearly, if one samples the region at random by applying the operator to a series of random points, it will take define kf. Power of quantum superposition and entanglement. However, fewer functions calls are required. Let's pick an initial state in position basis, such as this, for a quantum computer with continuous spectrum at random. We need a suitable unitary operator, which can take the initial state to the final state. Okay, just as we have the Hadamard transformation in discrete computation, one of the basic operations with continuous variables is the Fourier transform between position and momentum variables in phase space. By defining the Fourier transformation as an active operator on n QNAT states, we can write it as like this, where xy equals, okay, and both x and y are in the position basis. This has been used by one of the present authors in developing an error correction code for continuous variables. This Fourier transform can be straightforwardly applied in physical situations. A set of modes of the electromagnetic field is simply an eigenstate of the Suppose we apply the unitary operator f to a basis state x sub I, then the relative amplitude of finding the system in the target state xf. Okay, so now the probability of finding the system in the final QNAT states will be given by the next operator. So whatever that means, all I read is that the Fourier transform is used. The next operator we need is the unitary operator, which can invert the sign of a basis state. We can define why. We can define the selective inversion operator for a continuous basis, where is the projection operator for continuous variables. Unlike the discrete case, we cannot define the projection operator for the basis x as this, because the operator px is an ill-defined and it will not satisfy the correct projection operator. What? The reason for this definition is that we cannot project an arbitrary state which is represented in terms of continuous basis states into a point to get the exact eigenvalue. There will be always a spread within an interval. We can only project a state around x0 to selectivity. It's not possible to design a device to make a perfectly selective measurement of a continuous variable. The interval x1, x2 cannot be narrowed down because it will always contain an infinite number of eigenvalues. Does this mean that you cannot squeeze to the extent that it's just going to be just like a spike at that point? Maybe that's what it means. I don't know. Thus, if we have a wave packet, the effect of projection is to truncate it around x0 within an interval. This operator satisfies this. With the help of the above inversion operator, we can construct a compound search operator. Okay, so here we've got like Is this the identity? Fourier transform, the inverse of the Fourier transform. Where am I? It may be remarked that the selective inversion of the target state can be achieved by attaching an ancilla QNAT. Selective inversion. Oh no, this is inversion. This is not. Oh no. Identity? I don't know. Can be achieved by attaching an ancilla QNAT and considering the quantum XOR circuit for continuous variables. If a quantum circuit exists that transforms XA into okay. Then by choosing the ancilla state, I'm here. We can selectively invert the state X for which f x equals 1. First we show that the section it's either too early right now or that's really dense. Let us define the state. Now we can show that the operator C can preserve the two-dimensional subspace spanned by states. First we show the action C on that. Then we can this can be expressed as blah blah blah. Using these new facts we can simplify the above equation. Similarly we can evaluate the action C on. Thus the operator C creates superpositions of two QNAT states, just as Grover's operator creates superpositions of two qubit states. Once we understand the action of C on QNATs, we can obtain the total number of steps required in reaching the target state. Here we use geometric structures from a projective Hilbert space of a quantum system to obtain the number of steps. But I'm not interested in obtaining the number of steps. I want to see generally what's generally the during the quantum searching with continuous variables, we want to reach state xf from initial state xi. This means we have to travel a shortest distance between these states, which is given. I guess here they just go ahead and they try to find the number of steps that you need. Initial base short distance, therefore blah 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 blah. Quantum computer based on QNAT can take applications of C. I'm not interested in knowing how many steps this can take me right now. Now we know that the quantum search algorithm over continuous variables is robust to some extent. Instead of the Fourier transform, if we replace it by a generalized Fourier transform and the search operator C, still the algorithm works. We do get a square root reduction. Doesn't matter. GFT with a flexible angle gives a physical change of the basis x by any desired amount. Here it should be mentioned that that's probably the rotation operation in Xanadu, right? So the search operator with this GFT takes the following form. Fourier transform something, Fourier transform minus something. We can see that the action of the generalized search operator on the initial state. So this is it. So this is basically the. So here, what the paper says, what the author says is you can generalize it to like a parametrized rotation. I guess that's what they say. The thing is, what are those operations? This IXF and IXI. This I didn't catch. That's what I'm kind of missing. That's the video before for the link. So here. Not convinced. Similarly, the action of the generalized search operator can be calculated like this. Now we can calculate the Fubini study distances to know how many steps. So in conclusion, we have for the first time provided an efficient algorithm such as quantum searching to be implemented on a quantum computer with continuous variables. The key elements of the generalization are Fourier transformation and inversion operators. So those are inversion operators. Okay, so now I need to understand what those translate to, and see if that somehow is close to what I got here, and whether this makes sense at all. Because if so, it gives me a neat explanation of, or it gives me some interesting insight about Kerber's algorithm, which is that it's not about, it's really not about where the way that I approached the previous my original breakdown of the algorithm was like, you know, look, so you're applying the Hadamard gates first, then you're doing something, and then you're trying to go back to your original state, but you cannot because you've changed something in between. But really, I think what's happening in here is it's the fact that you're using the two different dimensions, right? Like the two different observables. Um, I don't want to call it that you're using the two different observables. You're kind of using the two different dimensions to do the calculation. Just because of the way those dimensions behave at a quantum level, uh, which is this kind of thing when when you've got certainty in one place, you've got uncertainty in the other place. So that's the idea here is that if you're able, if you it's Grover's is then in this case it just means it's the mechanism to move information around the two dimensions. That's all it means. That's all it is. Um, and I'm talking about computational dimensions. I'm talking about in the discrete quantum computing, the x and the z observable dimensions. Um, Here I'm talking about x and p, position and momentum, because that's all what's happening here really. Uh, that's all that's happening here. Settings to h value. The black box doesn't matter. That's my point. The implementation of the black box doesn't matter. And the thing is, it's funny here because you don't have you don't have to deal with the different amplitudes of the possible outcomes. You just deal with that function, right? So the inversion about the mean geometrical explanation is a bit trickier, and I think here they use integrals for that, but that's what I think. But so I need to understand a bit more what do they mean by these, if these are these inversion operators they talk about. So inversion operator, the Hadamard transform in the case, and a suitably generalized inversion operator we construct. Okay, the inversion operator requires the projection of the inversion operators that the entire C requires the projection operator for continuous basis states, which we discuss. Oh no, okay, so that's the inversion operator. The next operator we need is a unitary operator that we can invert the sign of a basis state x. We can define the selective inversion operator for a continuous basis like that. Okay, but then just the mathematical definition of it. Projection operator for continuous variables, and like okay. And uses a projection operator for continuous variables. Unlike the discrete case, we cannot define the projection operator for the basis x as px because the operator is. So this is an integral. Yeah, this is just the mathematical definition then, so they can go ahead with the calculations later on to make the reasoning, which is kind of makes sense, but I'm not sure what this does really at the practical level. So how would that translate actually into quantum gate? Surge operator. And so, and is this compound surge operator the actual whole thing, or is it then, is this something that's used in conjunction in a combination with the Fourier transform? Does this already include the Fourier transform? That's what's not clear either here. That's what's not clear, because basically this says apply the Fourier transform, do this inverse, apply another Fourier transform, and change the sign, right? Which what we kind of do is like squeeze this place and that is, I mean, that I don't know. Fourier transform, because the F transpose and the F, I'm assuming, are the same thing, are equal. I'm assuming. Okay, let's. No, I need to sleep on this. I need to go through maybe. It's a combination of kind of these again. Maybe. Maybe what I can do the next video is I can try to compare that to Grover's algorithm's mathematical description a little bit, roughly see where the similarities are, see what this takes me. But I'm not yet sure that's the right thing, which bothers me a bit, but I really want to go through this. And it's not clear to me whether that's the whole thing, whether that the search operator sees the whole thing is the actual algorithm, and then you just repeat that operator many times, or is it something you have to use in conjunction with the Fourier transform or something like that still? That was kind of not clear yet here. I don't know. We'll see. We'll see.